Hi again. We continue our review of Module 2. The next topic that we want to discuss as a review is the topic of lubrication approximation. If you remember, we noticed that Navier-Stokes equations are relatively hard to solve. We found out that when fluids are very viscous and Reynolds numbers are usually much smaller than 1, in those cases we can actually deal with something simpler. Equations become linear. We had the Stokes equation, and we could actually make some theoretical or analytical progress for certain problems which have simple geometries. Geometries with certain embedded symmetries, like flow past a sphere, or flow on a, for example, infinitely long flat plate. The type of problems we dealt with, like Couette or Poiseuille flow or combination of them, have relatively easy geometries. Yet there is a big class of many different problems in fluid mechanics where the geometry that is given to us is relatively complex, and we need to find some kind of solution for those problems. We found that it's not really easy to find an exact solution to Navier-Stokes equation in an analytical form for those complex geometries. However, there are in many of these examples certain criteria or certain limits that are usually valid, and using those criteria and those limits, we can simplify equation of motion to some approximate version or some approximate equation that can be easily solved and can help us to get approximate solutions which are relatively very accurate and very much close to what we could have got with numerical solutions or other type of experimental observations. And that's the topic of lubrication approximation, and let's go through some of those examples. For example, we told you guys that there are two different classes of lubrication problems. The lubrication problems in which the viscous oil is confined both at the lower wall and upper wall by a solid geometry, like the slider block example, or the lubrication problems where at the lower side we have a solid wall, but at the upper side the viscous oil is just in contact with something inviscid, or something not anymore solid, a liquid or a gas in this case, like air. In this type of, in these two different canonical examples or types of lubrication problems, certain things are common, but there is also a small subtle difference that is good to keep in mind. Let's think about things that are in common. The first thing that both of these problems have in common is the fact that the length scale usually in one direction, for example here vertical or y, is much smaller than the length scale of the problem in the x direction. Usually these problems are geometries that are having long aspect ratios, and they are usually thin slender-like films of viscous oils or thin slender geometries. So you have the fact that these drawings, I should say, they are drawn exaggerated, so they look like h is also considerably large, but in reality h is much smaller than L. So if the L is, for example, the length of the slider block, which is the dominant length scale in the x direction, that length scale is much larger than the gap that we have under the slider block, which is captured by the scale h. Similarly here, the free surface lubrication example, the length of the free surface running down a ramp due to gravity, which is captured by L, is much larger than the thickness or the height of this film, which is captured by h. So this is the starting point that we usually go through our calculations. From this, we found out that there will be a corresponding mismatch between velocity components, and that's using conservation of mass or continuity. And we found that very soon we can say that if Vx scales as u, this u becomes much larger than a scale for velocity in the y direction, which if we call it v, that would be a scale for vy. And how much is larger is an order of L over h larger. So that was a result that we got from continuity equation. We don't want to go into details, but we showed that with three criteria. First is this aspect ratio, h squared over L squared, a geometrical aspect ratio, being much smaller than 1. The second criteria is a Reynolds number based on h multiplied to this geometrical aspect ratio, again h over L, much smaller than 1. And the third or the final criteria that we usually check when the problems have a transient or unsteady nature. H squared divided by kinematic viscosity nu multiplied to tau c, which is the characteristic time of the transient behavior of the geometry or the problem, if this also is much smaller than 1. If these three criteria, if these are met, we can actually make progress and use approximate equations, which we call lubrication approximation. Let's write them down. So we said that in the x component of lubrication approximation, we usually have 0 on the left-hand side because all the inertia terms are negligible because of the second criteria here. And the third one will help us to get rid of, this helps us to get rid of the advective terms on the left-hand side. This one helps us to get rid of the transient terms on the left-hand side. So the left-hand side will be approximately 0. On the right-hand side, we have the pressure gradient, negative dp over dx. We have the viscous term, which is mu d2 vx dy2. The dominant one will be the gradient with respect to y because of this criteria. And sometimes we also need to worry about the gravitational force per unit volume, rho g, and the component of that in the x direction, which is captured by rho gx term here. In the y direction, we saw that the approximate equations lead to a very simple balance that in the y direction, the momentum equation simplifies to nothing other than a hydrostatic type relationship for pressure. So gradient of pressure plus rho component of g in the y direction, which I use gy here for that. Rho gy multiplied to y. The whole combination, partial derivative of that with respect to y is approximately equal to 0. Now, these two set of equations should be able to help us solve the problems in both for both confined and free surface lubrication. What, however, we showed, and that's the part that these two become slightly different, is the fact that in this type of problems that we deal with, in free surface type of problems, we really don't have any mechanism to generate large pressures or pressure gradients. Why? Because at every point you reach this point, and with a small hydrostatic change in pressure, you reach a point that has exactly or very similar pressure value of pressure compared to ambient pressure outside. So you cannot really generate large pressure gradients here, and it's the gravity or some other term or parameter that is really balancing the large value of viscous stresses. So in both of these problems, viscous stress is the dominant one. The question is whether gravitational or something equivalent to that can balance these viscous stresses or the pressure gradient. In free surface lubrication is the gravity. So in free or open surface lubrication, what we get is 0 is approximately equal to the gradient of velocity in terms of that is incorporated inside viscous stresses, and then another gradient of that, so mu d2 vx dy2, viscous stresses per unit volume, plus rho g x should be equal to 0. So this is the approximate solution that approximate equation that we need to solve. And they usually give rise to velocity profiles that if you plot them, they would be almost like a half a parabola. So they are Vx as a function of y is going like this. And this is basically the height of your free surface. And if you like to think about what really is happening here, if you are a fluid element sitting here, the gravitational effect is pushing you downward, and the friction that you have because of your motion and the gradient of the velocity, the viscous friction, is balancing this gravitational force that is pushing you or pulling you downward. However, in the other case, in the case of confined lubrication on this side, we saw that actually we have a different balance. So in confined lubrication, we have the fact that often we don't really have any gravitational element, or we can easily see that there is a pressure gradient generated, because not anymore we have a free surface on the top. We have another solid geometry. So we have a mechanism to generate large pressures and large pressure gradients. And that tells us that this equation simplifies to 0, being approximately equal to mu d2 Vx dy2 minus the pressure gradient, which is dp dx. So this is the approximate equation that we have in these cases. These simple approximation will already tell us something very important and useful in lubrication problems. The simple approximate version of lubrication equation tells us that viscous terms which scale as mu u divided by h squared should scale with the pressure gradient, which scales as the characteristic scale for pressure Pc divided by L. This simply suggests that in confined lubrication problems, the characteristic pressure you generate between the two solid geometries or boundaries, Pc, scales as mu u over h multiplied to L over h. And this is an interesting result. It tells us that not only pressure is following a viscous type scaling. Remember, this is viscosity times the shear rate, mu u over h. It is amplified by a large factor, large geometrical factor that is set by L over h. And that's the reason these geometries are useful for lubrication purposes, because the coefficient of friction, which is the ratio of the friction or side or shear forces or stresses over normal or forces or pressure forces, which goes as a scale of wall shear stress divided by characteristic pressure, Pc, that usually scales with a geometrical ratio h over L, which is much smaller than 1. You can benefit from that in your design of truss bearings and other geometries because of this simple geometrical ratio that you obtain, which is much smaller than 1. So again, as a review, in this type of problems, we don't really have simple geometries to find simple solutions, analytical solutions to Navier-Stokes. We have to use this geometrical mismatch in dimensions sometimes for problems that have a large aspect ratio or a slender body type problems. And a consequence of that, combined with the fact that many times these problems involve oils that are relatively viscous, give us a set of criteria that if they are valid, then our equations of motion can be simplified to these two. And then for the free surface lubrication, we have to deal with viscous stresses being imbalanced by something like gravity. And in confined lubrication, we have pressure gradients being in balance with viscous stresses. In this case, we can develop really large pressures and pressure gradients. In this case, we have a simple balance of gravity or some other effect, like, for example, centripetal acceleration in a spin coating, pushing the fluids against the viscous resistance or friction.